Okay, hello everyone. Welcome to this lecture. In this lecture, we will continue our discussion regarding how to solve linear homogeneous recurrence equations. So, just to recap, in the last lecture, we discussed how to solve linear homogeneous recurrence equations for the case when the characteristic roots were all distinct, right? So, this was the summary of the discussion that we had in the last lecture. We had an equation of degree k. Okay, linear homogeneous recurrence equation of degree k, which is imposed by saying that tk is not allowed to be zero, and you may or may not be given the initial conditions. Now, first step will be to form the characteristic equation, which will be an equation of degree k, and then we find the characteristic roots. They may be real roots, complex roots, they may be all distinct, some of them may be distinct, some may be repeated, and so on. So, in total, we will have k roots, which we denote as R1 to Rk. And the case that we discussed in the last lecture was the following. If it turns out that all the k roots are different, then any sequence will be satisfying the given recurrence condition provided the nth term of that sequence is of this form. Namely, it is some constant times the first characteristic root power n plus constant times the second characteristic root power n and so on for some arbitrary constants alpha 1 to alpha k. Now, depending upon what are the constants you fit, you get different sequences satisfying the recurrence condition, right? So, this general form of the solution is irrespective of whether it satisfies the initial condition or not, right? If you want to satisfy the initial conditions as well, then you can find out the exact constant or the unique solution. So remember, if we are not bothered about the initial conditions, then there can be plenty of infinite sequences satisfying the same recurrence condition, and all of them can be obtained by this general form. Now, if you want to find out the unique sequence satisfying the initial conditions as well, then you have to find out the exact values of these constants alpha 1, alpha 2, and alpha k, which can be obtained uh, by utilizing the initial conditions if they are given to you. That's the idea, right? Now, in this lecture, we will discuss the case when the characteristic roots are repeated. And again, for simplifying the discussion, we start with the case when the degree is of when the degree is 2. That means the general form of the recurrence equation is this, where C2 will not be 0. Okay, and you may or may not be given the initial conditions. If you are not given the initial conditions, then we will end up with the general form of the solution. That means any sequence which will satisfy this sequence condition, what will be the general form or the nth term of that sequence, we will end up with that. But if you want to find out the exact sequence, then we have to utilize the initial conditions as well. Okay, so this was the theorem for the case when the roots were distinct, right? If the roots are distinct, then any sequence whose nth term is of this form for some arbitrary constants alpha 1 and alpha 2 will be satisfying the recurrence condition. But it turns out that the theorem no longer holds if the roots are equal, right? So we are considering the case when we have degree 2 characteristic equation, and hence we have two roots R1 and R2, and if R1 and R2 are same, then the theorem no longer holds. This is because if you recall the proof of the last theorem, then there, if we want to find out the exact sequence satisfying the given recurrence condition as well as the initial conditions, right? So for that, our constants alpha 1 and alpha 2 turned out to be these, right? This was our alpha 1, this was the constant alpha 1, and this was the constant alpha 2, and they are they were well defined for the case. They were well defined if they were well defined because for the previous case, your R1 and R2 were different, in which case the denominator will be non-zero. But if your R1 and R2 are same, then uh, these alpha 1 and alpha 2 are not well defined, and in which case we cannot find out the exact sequence satisfying the given recurrence condition as well as the initial condition. And if we can't find out the exact sequence from the general form, that means that general form which was applicable for the previous case is not applicable for this case. So that means the general form of the solution or the general form of any sequence satisfying the recurrence condition for the case of distinct characteristic roots will be different. So the theorem statement for this case is as follows. We can prove that if the characteristic roots are distinct, right? And say the characteristic roots are R1, R2 are same, so I denote the characteristic root as R0. It is the common characteristic root. Then this theorem statement basically says that any sequence whose nth term is of this form will satisfy the recurrence condition for some arbitrary constants alpha 1 and alpha 2. Right? Now again, this is the general form of any sequence satisfying the recurrence condition, and there could be infinite number of such sequences. So right now I am not utilizing the initial conditions. If you want to find out the exact sequence satisfying the recurrence condition as well as the initial conditions, then you have to solve the or you have to find the exact constants which you can obtain by utilizing the initial conditions if they are given to you. But if they are not given to you, then we end up with the generic form or the general term of any sequence satisfying the recurrence condition, and this will be constant times r0 power n plus another constant times n into the same characteristic root raised to power n. Right, so that's the difference here. In the previous case, if r0, if r1 and r2 were the two roots, then the general form was the first characteristic root power n and another constant times second characteristic root power n. My claim is that this general form is not applicable for the distinct root case. The general form will be now this, and the proof can be shown similar to the way we proved the theorem for the case of distinct roots, right? There we utilize the fact that R1 and R2 are two distinct roots of the characteristic equation, and then we showed that whatever general form was there, it satisfies the recurrence condition. The same we have to do in this case as well, and we have to utilize the fact that we have equal roots for the quadratic equation, right? So the part one of the proof will be we have to show that any sequence whose nth term is this, irrespective of what is the value of the constant alpha 1 and alpha 2, will satisfy the recurrence condition that a of n is equal to c1 times a of n minus 1 plus c2 times a of n minus 2. And we can prove that very easily. And the second part of the proof will be that if at all this sequence whose nth term is this satisfies the recurrence condition as well as the initial conditions, then we can find out the constants alpha 1 and alpha 2. They are well defined, right? So now the form of the constants alpha 1 and alpha 2 will be different from the form of the constants alpha 1 and alpha 2 which were there for the case of distinct roots. Now the alpha 1 and alpha 2 will not be the same. Specifically in the denominator, in the earlier case we had r1 minus r2 which was non-zero, but now the form of alpha 1 and alpha 2 will be different for this case. And the proof is very similar to the proof for the case of distinct root case. So I am not going into the details. You can easily do that, right? So that will be the that's a general form here. So let's see an example for this case. So suppose I want to solve this recurrence condition, and for the moment ignore the initial conditions, right? So the first step will be forming the characteristic equation. The characteristic equation will be of degree 2. My C1 is here 6 and my C2 is this. So accordingly, I get the form of the characteristic equation. The characteristic equation will be r square minus 6r plus 9 equal to 0. The next step will be finding the characteristic roots, and in this case the characteristic roots are same, namely 3 and 3. That means the general form of the solution will be constant times 3 power n plus another constant time n into 3 power n, right? This will be the general form of the solution. Now, substituting different values of alpha 1 and alpha 2, you get various sequences satisfying the recurrence condition. In fact, if you substitute alpha 1 equal to alpha 2 equal to 0, that will give you one sequence, namely a sequence where all the terms are zeros. That's a sequence satisfying the given recurrence condition. If you satisfy alpha 1, if you substitute alpha 1 equal to say 1 and alpha 2 equal to 0, then that gives you a sequence where the nth term is 3 power n, and you can verify that a sequence whose nth term is 3 power n also satisfies the same recurrence condition. So by substituting different values of alpha 1 and alpha 2, you will get different sequences satisfying the recurrence condition. But now, since we are also given the initial conditions, we will be interested to find out the exact sequence satisfying the recurrence condition as well as having the initial terms 1 and 6. So for that, I will be substituting n equal to 0 here and n equal to 1 here, right? And get a0 equal to 1, a1 equal to 6, which will give me now two equations in alpha 1 and alpha 2, where alpha 1 and alpha 2 are my unknown constants. And by solving those two equations, I will be able to find out the exact alpha 1 and alpha 2, and hence the exact sequence satisfying my recurrence condition as well as the initial terms. Right. So that was the case of degree 2 characteristic equations with repeated roots. Now we will consider the general case where we have a linear homogeneous recurrence equation of degree k with repeated roots. Okay, so this will be the form of the recurrence equation. You may or may not be given the initial conditions. If you are not given the initial conditions, we will just end up writing down the general term of the sequence satisfying the recurrence condition. But if you are also given the initial conditions, you can find out the exact sequence satisfying the initial conditions as well as the recurrence condition. Right? So the first step here will be forming the characteristic equation, which will be an equation of degree k, and hence it will have k characteristic roots. Some of them might be distinct, some of them might be same, and so on. So what I do here is I denote the distinct roots by R1 to RT, right? And they occur with multiplicities M1 to MT respectively. That means the root R1 occurs M1 times, the root R2 occurs M2 times, and like that the root RT occurs MT times. Right? Now what's the relationship here? Each of these values M1, M2 and M of t are greater than equal to 1 because these are the distinct roots. So R1 will be occurring as a root definitely at least once. So that's why M1 will be at least 1. Of course, it might be possible that I have two roots, namely R1 and R1, in which case M1 will be 2. Or I might have a case when the only root is R1. That means in that case M1 will be k and so on. So number of that means depending upon the number of times R1 is occurring as a root determines the value of M1. Since R1 is occurring as a root definitely at least once, M1 will be at least once. Similarly, M2 will be at least one, and similarly M of t also will be at least one. So that justifies that why each Mi is greater than equal to 1. And the second condition here is that the sum of all the multiplicities here will be k because you have total k number of roots. So R1 will be occurring certain number of times as root, R2 is occurring certain number of times as a root, and R of t is also occurring as a root certain number of times, namely M of t number of times. If I sum of all these multiplicities, that should give me the total number of roots, namely k. That's a relationship between these multiplicities and the various roots. Now, what the theorem basically says is the following. The theorem says that any sequence whose nth term is of this form will satisfy the recurrence condition. Right? So let's decode this complicated looking general term here. So what's the first term here? The first term is basically a polynomial of degree m1 minus 1 multiplied by the first characteristic root raised to power n. Why m1 minus 1? Because the first characteristic root, namely r of 1, occurs m1 number of times. So that's why a polynomial of degree m1 minus 1. So that means if r1 occurs as a root only once, in that case m1 would have been 1, in which case this polynomial of degree m1 minus 1 is nothing but a constant. So in that case it will be constant times r1 power n. But if m1 is say 3, that means r1 occurs as a root 3 number of times, then this polynomial, the first polynomial here, will be a polynomial of degree 2 multiplied by the first characteristic root power n. The constant, the coefficients in this polynomial of degree m1 minus 1, they are all unknown constants. We can substitute any value for them, and that will determine a sequence satisfying the recurrence condition. The next term in this general term will be an unknown polynomial of degree m2 minus 1 multiplied by the second characteristic root power n. And like that, the last term will be a polynomial of degree m of t minus 1, because the last characteristic root, namely r of t, has multiplicity m of t. So it will be raised to power n, and it will be preceded by a polynomial of degree m of t minus 1. Right? So all these alpha values, they are constants here, unknown constants. Right? By substituting various values for these alphas, you get various sequences satisfying the recurrence condition. Now, if you want to satisfy the initial conditions as well, then you can substitute the values of n equal to 0, n equal to 1, and all the way n equal to k minus 1. You get various equations in these unknowns alphas, and you can get the exact alphas satisfying the initial conditions as well as the recurrence condition as well. Okay. Specifically, how many alphas will be there? You have in the first polynomial you had m1 alphas, right? M1 constants. Second polynomial you had m2 alphas, and like that the last polynomial you had m of t alphas. So total how many unknowns are there? M of 1, m of 2 plus m of t, which is nothing but k. So you will be having k unknown constants here, and if you are given k initial conditions, namely v0, v1 up to v of k minus 1, by substituting n equal to 0, n equal to 1, n equal to k minus 1 in this general formula, you get k equations in k unknowns. By solving them, you get the exact constants. Right? And now you can tally that this general formula uh, captures all the cases that we had discussed till now, right? So if you are in the case when all the roots are distinct, that means you have k roots. Each of the roots has multiplicity 1. That means m1 is 1. That means r1 occurs as a root exactly once. M2 is 1, that means R2 occurs as a root exactly 1, and like that M of k is 1, that means R of t occurs as a root exactly once. Then each of these polynomials will be a constant polynomial followed by that characteristic root raised to the power n, and that's precisely was the general form of a sequence, or the nth term of the sequence satisfying the recurrence condition for the case when all the characteristic roots were distinct. Right? So you can easily verify that. The proof for this theorem will be again similar to the case where we took the degree 2 equation and the roots were distinct. I am leaving the proof for you. Okay. So now let's see an example for applying the general formula. So imagine you are given this recurrence condition. For the moment, assume you are not given the initial conditions. Right. So the first step will be forming the characteristic equation. The characteristic equation will be this. It is a cubic equation, so it will have three characteristic roots, R1, R2, R3, right? It turns out in this case that R1 and R2 and R3 are all same, and hence the multiplicity here is 1. You have only one characteristic root occurring. thrice. So your multiplicity is 3. So the general solution will be a unknown polynomial of degree m1 minus 1, namely 2, multiplied by the characteristic root raised to the power n. And the characteristic root here is minus 1, so that's why minus 1 raised to power n. That will be the general solution. By substituting different values of this alpha 1 0, alpha 1 1 and alpha 1 2, you get various sequences satisfying the recurrence condition. Now, since you are also given the initial condition, you can find out the exact sequence satisfying this initial conditions. That means they start with the terms 1 minus 2 minus 1 and the nth term satisfies the recurrence condition. That you can do by substituting n equal to 0 here, n equal to 1 here and n equal to 2 here in this general form, and whatever expression you obtain, equate it with 1, minus 2 and minus 1. By doing that, you will obtain three equations in this three unknown constants, alpha 1 0, alpha 1 1, alpha 1 2, and you get the exact value of these constants and hence the exact sequence satisfying the recurrence condition. Okay, so that brings me to the end of today's lecture. These are the references used for today's lecture. Okay, just to summarize, in this lecture, we continued our discussion regarding how to solve linear homogeneous recurrence equations of degree k, and we consider the case when the characteristic roots are repeated. Thank you.